This is Dr. Anthony Revis, and this is SVSU, General Chemistry 111, Chapter 5, Lecture 1. That's Lecture 1 of Chapter 5 on Thermochemistry. This chapter will cover 3 topics. It will cover energy basics, calorimetry, and enthalpy. These topics will be covered, but they might not be covered in this order. Let's start with some basic definitions. First law of thermodynamics and the law of conservation of energy. The law of conservation of energy states, during a chemical or physical change, energy can be neither created nor destroyed, although its form can change. In other words, you cannot create nor destroy energy, but it can be transformed into another form of energy. The first law of thermodynamics states that if heat is recognized as a form of energy, then the total energy of a system plus its surroundings is conserved. In other words, the total energy of the universe remains constant. In other words, the amount of energy that's in the universe right now is the amount of energy that it has and will have for as long as we can perceive. Energy does not change. It remains constant in the universe. Now, when we start to think about energy, there are some types of energy or forms of energy that we have to get some understanding of how it's defined in order to carry on a discussion about it. So let's take a look at energy in these types that we have listed on this slide. One basic definition of energy is it is the capacity to do work. When we do work, that's energy. And it takes energy to do work. You pick up an apple, it requires energy. That energy does work. Okay? So that is the basic definition of energy. Energy is the capacity to do work. Now let's look at the types of energy that we can have involved in producing that work or doing that work. One form of energy is radiant energy or radiation energy. Radiant energy comes from the sun and is the Earth's primary energy source. We get our energy directly from the sun on a daily basis, whether it's what we call sun up or sun down. The energy of the sun is what sustains our biosphere, what sustains the Earth. The sun emits what's called electromagnetic energy. It's both electric properties and magnetic properties. And that electromagnetic energy travels on a wave with particle properties. So electromagnetic energy has both wave and particle properties. We'll talk more about these concepts in other lectures. Thermal energy is the energy associated with random motion of atoms and molecules. Atoms and molecules are in motion. The energy from that motion is what's called thermal energy. The word heat is most often used for thermal energy. Chemical energy is the energy stored within chemical bonds of a substance. Stored energy is potential energy. In other words, there's potential energy in the food you eat, in that potato, in that vegetable, in, if you're a meat eater, that meat, in the grain. There's potential energy in the bonds of that substance. And that chemical energy is released under some conditions. Okay? In your body, metabolism. Some form of metabolism, digestion, what have you. That's when we release that energy. There's nuclear energy. Nuclear energy is the energy stored within a collection of neutrons and protons in an atom. In other words, nuclear energy comes from protons and neutrons. Subatomic particles produce nuclear energy. That energy is used most often today in plants, in power plants. There's potential energy. Potential energy is the energy available by virtue of an object's position. An object at rest has potential energy. A coffee mug on your desk has potential energy. You sitting in a chair have potential energy. A boulder on the top of the hill has potential energy, although that potential energy is less than the potential energy of a boulder sitting at the bottom of the hill. But nonetheless, where an object is positioned determines the amount of potential energy. And then there's kinetic energy. Kinetic energy is the energy due to the movement of the object. An object in motion has kinetic energy. Tossing a tennis ball or a baseball or a football, that is kinetic energy. The ball in your hand has potential energy. When that ball is tossed, it takes on kinetic energy. So you can have something with potential energy if it's at rest. But when that object is in motion, it will have kinetic energy. So these are the energy forms that we like to expose you to. Some of these will be talked about in more detail in today's lecture, and others will be in future lectures. So you do well to memorize these definitions. Radiant energy, that's electromagnetic energy of the sun. Thermal energy, that's the random motion of atoms and molecules. Chemical energy, that's the energy stored inside the substance. Nuclear energy, protons and neutrons. Potential energy is at rest energy. Kinetic energy is an object in motion energy. Let's consider some other definitions and start to put these definitions to work. Heat is the transfer of thermal energy between two bodies that are at different temperatures. Heat transfers from hot to cold. If there's a hot body, and we'll talk about what hot means and what cold means. If there's a hot body, it would transfer from the hot body to the cold body. Okay? The general principle here is that it flows from higher energy more freely to lower energy than it does the opposite direction. So that's a general principle to keep in mind when we start to talk about thermodynamics. You want to start to think about it as energy, high energy or higher energy, and low energy or lower energy. Okay? So heat is a transfer of thermal energy between two bodies that are at different temperatures. And the heat travels more freely from hot to cold. Temperature, on the other hand, is a measure of that thermal energy. Okay? So temperature is not exactly thermal energy. It is the measure of the thermal energy. It measures the average kinetic energy of the substance. So if you want to know the average kinetic energy of a substance, you take its temperature. It's very important to note that temperature does not equal thermal energy. That is an important thermodynamic principle for you to know and remember. Temperature and thermal energy are not the same. Temperature measures the thermal energy. Temperature itself is the measure of the average kinetic energy of the substance. So let's reiterate a few important principles to understand about this thermal energy and temperature. Again, thermal or heat energy is a type of kinetic energy, and it is associated with the random motion of atoms and molecules. And that's important. The random motion of molecules and atoms is read by a temperature. It is the measure of its thermal energy. Temperature is the quantitative measure of hot or cold. If you want to know what is hot or cold, you take its temperature. Now, when we think of the idea of hot and cold, fast-moving molecules have higher thermal energy. They're said to be hot. When it's high thermal energy, we call it hot. Slow-moving molecules have lower thermal energy, and we call it cold. So when there's lower thermal energy, it's cold. When it's high thermal energy, it's hot. That's how we define these terms. And so when we say something is hot, that means that it has fast movement of the molecules. When we say something is cold, it has slow movement of the molecules. And that's an important principle to retain. These concepts and ideas and principles about energy, and in particular about thermal energy, about energy in chemical bonds, kinetic energy, potential energy, and really a look at energy in general, is often examined under the heading of thermochemistry. So what is thermochemistry? Thermochemistry is the study of heat change in chemical reactions. So when we talk about thermochemistry, we think about heat change in chemical reactions. Recall again that chemical bonds have energy, they have potential energy. Heat energy involves thermal energy. We can have potential energy that's transformed into kinetic energy. But when we study this particular area, it is called thermochemistry. The study of thermochemistry involves the examination of systems within a universe. And what does that mean? The system is a specific part of the universe that is of interest in the study. In other words, we have this universe, much like the universe we live in, and there's a part of that universe that you're interested in studying, like the Earth, like the stars, like the planet, other planets. These are parts of the universe that are of interest of study. Thermochemistry tends to examine these areas of thermochemistry related to systems within a universe. So we have to define what that system is going to be. And this will start to make more sense to you when we start to share more examples. Right now we're trying to expose you to the concepts, the language, and some key definitions that are important. So let's take an example here. Water in a container. So you have, in this illustration, we have 3 water containers. The water containers are the system that we want to study in this universe. Contained within these containers is water. There are 3 conditions under which we might examine this water container. One condition would be an open. The other would be closed, and the other would be an isolated system. Each of them would yield a different result. So for these 3 systems, we should expect 3 different results with regards to its energy. For example, under the condition of A, we have water within the system. We can have heat transfer across the container walls. We could also have a vapor escaping from the open system, the open vessel. In that case, we'd have exchange of mass and energy. That would be different from a closed system where we would only have heat transfer across the walls of the system. In a closed system, we would only exchange energy, but no mass would change. In the case of an isolated system, nothing happens. It's completely isolated. It sits there and it does not change. It does not interact with the universe. So, example of C, an isolated condition means that it is not interacting in a meaningful way with the universe. In the case of B, it is interacting with the universe, its surroundings, through exchange of energy. In the case of A, in the open system, it is interacting with the universe, with its surroundings, by exchange of heat energy and water vapor. So the question then is, how do we gain value from this understanding in the universe, in our surroundings with these systems? And how do we take advantage of the thermochemistry involved in these systems? Now, the answers are not always straightforward. However, we start by recalling that energy is the capacity to do work. So how do we harness this energy and put it to work? Okay? One of the ways scientists approach this is through the study of what's called thermodynamics. What is thermodynamics? Thermodynamics is the scientific study of the interconversion of heat and other kinds of energy. In other words, thermodynamics is involved with how we carry out interconversions of heat to other forms of energy from which we might be able to get work done. Okay? Energy is the capacity to do work. We want to transform energy forms into a form that can produce that work. When we think about thermodynamics, there's a term called state functions that's important. Let me give you the definition and then we'll talk about what that means. State functions in thermodynamics are properties that are determined by the state of the system. And that's what it means, the state of the system, regardless of how that condition was achieved. Energy, regardless of how you got the energy, that is the state of it. Pressure is a state function. It is in that state. Volume, it is in that state. Temperature, it is in that state. In other words, the energy is what the energy is. The pressure is what the pressure is. The volume is what the volume is. And the temperature is what the temperature is, regardless of how it got there. And that's important to know, that it will have those physical properties regardless of how it got there. It will be energy, it will be pressure, it will be volume, it will be that temperature. Okay? That brings us back to the first law of thermodynamics, which states again that energy cannot be destroyed nor created, but it can be converted into other forms. Now, when that conversion occurs, the energy of the system plus the surroundings must be balanced to equal zero. In other words, what comes into the system must balance with what goes out of the system. If the system is positive, then the surroundings must be negative. They must balance out. What's released to the surroundings must match what enters the surroundings. So there must be balance. Chemical energy lost by combustion, for example, from the system must equal the chemical energy gained to the surroundings. That is what the laws of thermodynamics dictate. Why is that important? Therefore, we can talk about how, when we generate energy in a system, how to transform that energy into a useful form into the surroundings and vice versa. Because the key principle is that it will be balanced. So if we know the energy released, we know the energy gained. And therefore, we can do convenient calculations to determine how to use this energy to do work. So, another form then to look at the first law is to say that the change in the internal energy of the system is equal to the heat exchange between the system and the surrounding and the work done on or by the system. In other words, the heat exchange for the internal system is balanced against the heat exchange between the system and the surroundings and the work done on or by the system. So this is where we get the formula delta U, the system, equals Q plus W, where again delta U is the change in the internal system, okay? Change in the energy for the internal system. Q is the heat exchange between the system and the surroundings. And W is the work done on or by the system. This can be rewritten in the form of work equals minus P for pressure delta V, which is the form of the equation that we can manage under laboratory conditions. So we can use this form of work equals minus P delta V to produce work, because we can add or decrease pressure, or we can add or decrease volume. And from that addition or decrease of pressure or volume, or actually the change in volume, we can then calculate the amount of work produced. This table, table 6.1, shows you some signs that this work will have under certain conditions. Work done by the system on the surrounding will be a negative sign. Work done on the system by the surrounding will be a positive sign. So knowing these signs helps you understand what's happening. Is the work being done on the system, or is the work being done on the surroundings or by the system, and vice versa? Heat absorbed by the system from the surroundings is an endothermic process, which you will be learning in this lecture. It means that it has a positive value. When we have an endothermic positive value, that is written on the left side of balanced equations, which you will also be learning. Heat absorbed by the surrounding from the system is exothermic, is negative, which means heat is going into the system is exothermic, and if it involves a chemical reaction, then that energy is written on the right side of the equation, which you will also be learning. So these are the signs that tell you what's happening to the system. You do well to memorize these. Another way to express this law and to look at what's called as enthalpy is to again recognize that delta U, which is the change in the internal energy of the system, is equal again to the heat plus the work. Now at constant pressure, heat equals delta H, which is our term enthalpy or change in enthalpy. Occasionally when people are talking about change in enthalpy, they would simply say enthalpy. So be aware of that. Be sure you take a look at the symbols when you hear that. So you'll hear people that will say it's enthalpy when they really mean the change in enthalpy. And that is the common language to the science, and scientists tend to know when they're talking about which. Okay, so just be aware of that. So at constant pressure, heat equals to the change in the enthalpy. And we know that work equals minus P delta V. So we can work through these equations to discover that our change in enthalpy is related to the change in the internal energy plus pressure times the change in the volume. And we show you this diagram to say that on the left side, we start with pressure. If the volume changes, delta V allows us to experience a change in delta H. And that's important to know. So, when the volume changes, so does delta H. So delta H goes as pressure goes, if you will. Okay? Now, as we continue to discuss this, you'll learn more about exactly what this enthalpy means. But it's important to note that this change in energy can be measured. From that change in energy, we can gain understanding about the work on the system or by the system, the heat into the system or the heat out of the system, or the energy into the system or the energy out of the system, based upon our understanding of these thermodynamic properties and these state functions. One of the useful ways to experience these thermodynamic properties, or the result of the thermodynamic property, is through what's called the heat of reaction, the enthalpy change. So, what do we need to know about the heat of reaction? There are three important parts to this. There are more, but let's talk about these three primary definitions and concepts that are important with regard to the heat of reaction. The heat of reaction is the amount of heat absorbed or released during a chemical reaction at constant pressure. During a reaction, heat is either absorbed or released. The heat of reaction measures that, or is a measure of that. If heat is absorbed, that means it's lost. So one will be positive and one will be negative. But recall that heat into the system must equal the heat out of the system. We cannot destroy nor create matter. So if you know there's a positive value going in, then you also know there's a negative value coming out. What else do we know about the heat of reaction? The heat of reaction is the difference in the energy of the reactants and the products, and that is a very basic fundamental rule of thermochemistry, of thermodynamics, of this type of chemistry, or this area of chemistry. The heat of reaction is shown by the symbol delta H. The enthalpy change is delta H. So delta H, put simply, equals H of the products minus H of the reactants. And these are values that we can find in tables or that can be experimentally determined. Now, before we start to use delta H to do calculations and determine these heats of reactions, determine these enthalpies, there are a few other concepts that we need to explore. The energy in a chemical reaction can either be released or absorbed. If the energy is absorbed, then it is positive energy. If the energy is released, then it's negative energy. Negative energy is exothermic energy. Positive energy is endothermic energy. So what is an exothermic process? And what is an endothermic process? An exothermic process is any process that gives off heat. It transfers thermal energy from the system to the surroundings. An example would be the formation of water from hydrogen and oxygen. Note that hydrogen and oxygen are both diatomic gases. Note also that this equation is balanced. The energy from this reaction is written on the right side because it is released. Exothermic energy is written on the right side. The first equation shows you how we form water from these two diatomics, and the equation is balanced. The next exothermic process is when water gas goes to water liquid. Energy is released. In other words, water gas has higher energy or is at a higher energy state than water liquid. Steam has more energy in it than water. And when the steam cools, it releases energy to the environment. That energy in a balanced chemical equation is written on the right side. Therefore, it is an exothermic process. It has negative energy. On the other hand, an endothermic process is any process in which heat has to be supplied to the system. The system needs to absorb energy from the surrounding in order to function. This is actually what happens in photosynthesis. The example shown here is where we take this mercury in the 2 oxidation state, oxide, and it is decomposed in a decomposition reaction to mercury 0 and oxygen 0 as the diatomic gas. This process of decomposing the mercury compound to the individual elements requires energy to be put into the system. Likewise, energy is required to go from a solid state of water to the liquid state. That's why you basically heat your water, boil your water to melt the ice, or just put the ice out in the sun. And so it goes from a solid to a liquid, and that means energy is absorbed, the energy is absorbed, and it transforms it into the liquid form. Same number of molecules and atoms. Energy is not destroyed, neither is it created, neither is matter destroyed or created. It's balanced. The universe works on a balanced system. Energy in must match energy out. When the energy is released or goes out, it's called exothermic. When energy is supplied to the system, then it's called an endothermic process. These diagrams are intended to give you an idea of what the energy levels look like in a relative sense. For example, the one on the left, which is an exothermic process, shows energy where we have hydrogen and oxygen at a higher energy state. It goes to give water, which is at a lower energy state. And as it moves from the gaseous hydrogen and oxygen, the two diatomic molecules, to the water liquid, note the states, gaseous state to a liquid state, there is a release of energy. That is an exothermic process. It goes from uphill to downhill, at the top of the waterfall to the bottom of the waterfall. So, exothermic processes go from higher to lower energy. Energy goes out of the system. In the case of an endothermic process, note that we have mercury and oxygen in a higher energy state than the mercury 2 oxide. In this case, energy from the surrounding is used to carry out the transformation from the lower energy molecule, compound, to decompose it to the liquid mercury and the gaseous oxygen. lower to higher energy, energy into the system. So let's summarize what we know about an exothermic reaction. In an exothermic reaction, heat is released. Delta H is negative. The energy of the products is less than the energy of the reactants. Heat is produced according to the equations that look like the one shown here for diatomic hydrogen and diatomic chlorine to give hydrochloric acid gas plus 185 kilojoules on the right side of the equation. However, when we write that and report that value as an exothermic value, delta H equals minus 185 kilojoules per mole. That is the heat release. So, for example, in a problem, if a reaction was written and it said it released 185 kilojoules per mole, what is its delta H? Its delta H would equal minus 185 kilojoules per mole because it's exothermic. So anytime you independently record the delta H of an exothermic reaction, you must note it as a negative value. However, when it's written in a balanced equation, it's written on the right side of the equation as a plus because. So how do we look at it as a diagram? How do we show this energy on an energy diagram? The exothermic reaction is shown on this diagram where the reactants are at higher energy. They're at the top of the waterfall, and the reactants go downhill to produce the products, 2 molecules of hydrochloric acid. The energy of the product is less than the energy of the reactants, and that energy is reported as a negative 185 kilojoules. Delta H is minus 185 for this exothermic process and is reported in kilojoules, which are the standard units for reporting such values. Enthalpy is reported in joules and kilojoules. Let's summarize what we now know about endothermic reactions. In an endothermic reaction, heat is absorbed. Delta H is positive. The energy of the products is greater than the energy of the reactants. Heat in an endothermic reaction is a reactant. It is part of what's put into the system. It is written on the left side of the equation. Therefore, we write it as a reactant. Follow? And it produces a product. The energy there then is positive energy, a plus 181 kilojoules for the reaction shown here of nitrogen and oxygen. On an energy diagram with the progression of the reaction going from left to right and energy going up higher, we note that we start with the reactants at a lower position on the energy curve. They're at the bottom of the hill, and they are pushed up to higher energy products. The energy of the product is greater than the energy of the reactant. Delta H in this case is a positive 180 kilojoules. And if you look at these side by side, you'll see the opposite values for, or at least opposite signs or opposite effect for exothermic and endothermic. So if you understand endothermic, exothermic will be, for the most part, the opposite. If you understand endothermic, then exothermic is the opposite. So we show you here some examples of endothermic and exothermic to expose you to how it is written in a balanced equation. Notice the sign of the exothermic and endothermic. In the case of an endothermic reaction, we don't actually write the plus sign. It's written here for emphasis purposes, so we typically don't write the plus sign. But if in your chemistry class you write the plus sign, you typically won't lose points for something like that. Okay, but here we're writing it just to emphasize that endothermic has a positive value and is positive. And exothermic, on the other hand, we always write the negative sign. We must write the negative sign for an exothermic reaction. So we now know that when we look at enthalpy, that enthalpy is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. So basically, the enthalpy of the products minus the enthalpy of the reactant gives us the enthalpy change. So that is what enthalpy allows us to do, to quantify the heat flow into or out of a system. At constant pressure, an exothermic reaction, endothermic reaction have opposite signs. The exothermic reaction, the product is less than the reactant. In the case of an endothermic, the product is greater than the reactant. Delta H is less than 0 for an exothermic. It is greater than 0 for an endothermic process. So that allows us to be able to carry out calculations to determine how much energy we can have available to do work with or to put to work. So let's do a calculation of delta H in this particular reaction. Here's the question. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams, actually 50.0 grams of ammonia, 3 sig figs? How much energy do we produce in this reaction? So we have nitrogen gas and hydrogen gas in a balanced equation. We know that it's balanced because we see the coefficients with 2 nitrogens on the left, 2 on the right, 6 atoms of hydrogen on the left, 6 on the right, balanced equation, to give us ammonia. And we note that the delta H is minus 92.2 kilojoules based on a standard table that we looked up. So how do we approach this problem? We approach this problem as we would any other mathematical problem in chemistry. We start with a given and carry out a dimensional analysis based upon the standard rules of math. So we write our given as 50.0 grams of ammonia times bar with the grams on the bottom and mole on the top. We know that we put grams on the bottom because our given has grams. That dictates the denominator of our first conversion step or conversion factor. That conversion factor goes grams per mole. We calculate the gram per mole of ammonia using the molar mass of nitrogen and the molar mass of hydrogen, 3 units of hydrogen. We then take this conversion factor and we further convert it to energy by taking moles of ammonia, and the next conversion factor will have moles of ammonia on the bottom because that is how dimensional analysis works. That's how we follow rules of math. And that goes to kilojoules. And if we check with cancel out, cross outs in math, we're left with kilojoules, which is exactly what we're looking for. So let me restate that. We take 50 grams of ammonia times 1 mole per 17.3 grams times minus 92.2 kilojoules per 2 moles of ammonia, because that is the ratio we see in the balance equation. If we look at the balance equation, we see 2 moles of ammonia in the balance equation plus 92.2 kilojoules of energy. We say plus that. If we note the bottom of the slide, we show you what the formal equation looks like. But since it is released energy, it is an exothermic process, that energy is negative. And therefore we obtain a negative 135 kilojoules. Some other conversion factors we just show you here that you want to be aware of that may come in handy for other calculations. We don't need to report these. We point this out to you so you're aware that any factors or variables in the balance equation may be used as conversion factors simply by paying attention to the coefficients and what that variable is. Occasionally, when we want to determine the energy or the thermal energy or the enthalpy or understand the thermodynamic quantities involved in a chemical reaction, we cannot find a single table with the single value we need. That brings us to Hess's law. And what is Hess's law? First of all, according to Hess's law, heat can be absorbed or released in a single chemical reaction or in several steps. In other words, the heat of reaction can happen in one step or several steps in the chemical reaction. When there are two or more steps in the reaction, the overall enthalpy change is the sum of the enthalpy changes of those steps, provided they all occur at the same temperature. And that is an important principle about Hess's law. It works when the reaction is carried out or the steps in the reaction at the same temperature, which is typical for most of the reactions. So Hess's law allows us to use the sum of steps in the reaction to obtain the enthalpy or delta H values. Here we show you a diagram of what that looks like. We show you an example here of where the overall reaction is to take graphite plus oxygen to produce carbon dioxide. In this case, we start with a half reaction of graphite plus, here we're using 1/2 mole of oxygen just for the math. We know that the standard equations use whole numbers for their coefficients. However, because these two steps are intermediate towards our final reaction, note our final reaction, carbon plus oxygen, do not contain them. We are permitted to do this as we're working through the mathematical calculations. So we have these two reactions that summarize the single reaction. We note that carbon plus oxygen gives carbon dioxide with a delta H of minus 304. We also note that hydrogen plus oxygen gives us water with a minus 242 kilojoules. We show where these lie on the energy diagram to help you understand the difference in the energy levels and the direction of the energy flow in this process. So these are the values we have here. So we can take these values then and we can work through the math to obtain the final enthalpy of this overall reaction or the heat of this overall reaction according to Hess's law. So what do? First, we arrange the given equations to place reactants on the left side and the products on the right. That is important. So you take a look at the process, the output, the desired output for the reaction, and you outline it where the reactants are on the left and the products on the right. This is something that should become intuitive to you, that reactants are on the left, products on the right. So we set this up. And the first one, we look at the standard values given for the first equation, and we note that this equation is written just as it appears in the standard tables. Therefore, we simply record the value of negative 304 kilojoules. In the standard tables for oxygen, on the other hand, we note that we have to reverse the equation in order to put the reactants and products on the desired sides. If we reverse the equations, we must also change the sign. Therein, the sign changed from a negative 242 kilojoules to a positive 243 kilojoules. Missing the sign change is perhaps the largest error that students make in freshman chemistry in Gen Chem, is forgetting that when you reverse an equation, you must reverse the signs. All right? Step 2. If an equation is multiplied to balance the coefficients, multiply delta H by the same value. In our standard table, we had the equation given with 1/2 oxygen in it. Note now we're going to balance that, which is also why earlier we didn't change it so that we could evaluate the math step by step. Okay? So now we multiply times 2 so that we can balance the equation, and we also multiply times 2 to balance the energy. Again, energy cannot be destroyed nor created. The energy level must be balanced, however. So if we multiply times 2, the rules of math dictate everything gets multiplied times 2, including the energy. We then take the equations, as we would follow through mathematical steps, combine the equations, and cancel any substances that are common to both sides, like you would cancel out in any other common mathematical equation. When we do that, we're left with an equation for producing carbon dioxide from carbon and water to give us carbon dioxide and hydrogen gas. And we sum the delta H values, the 2 steps, gives us a positive 180. And this is what Hess's law allows us to do. It allows us to combine equations to determine the delta H for an overall reaction process. We show you now some standard enthalpies of formation. We're not asking you to memorize this table. This table is simply for awareness, to let you know that there are tables that show many enthalpies of formation. And in cases where we don't have a particular delta H value, we can use Hess's law to obtain overall delta H for the reactions in question. So with that, let's recap some important concepts from this chapter. We now know that there are different forms of energy, and that these forms of energy do work. Energy is the capacity to do work. We also now know that heat is the transfer of thermal energy between two bodies at different temperatures. Heat transfers from hot to cold, higher to lower. We also now know that temperature, which measures the average kinetic energy of a substance, is not the same as thermal energy. If the molecules are moving fast, we have higher thermal energy, and it's said to be hot. When the molecules are moving slowly, it has lower thermal energy, and it's said to be cold. Thermochemistry allows us to study the heat change in chemical reactions involving systems and universe. We note that the energy of the system and the energy of the universe must stay balanced. Energy can be transferred from the system to the universe, or we note that the universe can be isolated, or at least the system can be isolated from the universe. Thermodynamics allows us to study these laws of thermodynamics in such a way that we can understand the heat values and the work done by the system or on the system. Those values, or at least thermodynamic values, are reported in either negative values or positive values if this work is done by the system on the surroundings, it is negative. If work is done on the system by the surroundings, it is positive. We note also that heat absorbed by the system is endothermic, is positive, and heat released to the surroundings is exothermic. Heat can be calculated, delta H calculated, by taking the H of the products minus H of the reactants. We can use dimensional analysis and conversion factors based upon balanced equations to obtain the values associated with heat released or heat absorbed. Hess's law tells us that if we cannot determine that in a single reaction, we can use combinations of reactions that allow us to mathematically calculate the final value of the single reaction based upon a summation of its partial reactions. And that does it for Chapter 5, Lecture 1 of Chapter 5 on thermochemistry.